Welcome back to The Explainer. If you're tracking the bleeding-edge intersection of deep physics and commercial reality, you are in exactly the right place. Today we're diving into a highly ambitious, 15-technology venture capital portfolio from Imagenta. And what unites all 15 of these assets? It's a massive, singular goal, using nanophotonics, quantum mechanics, and AI to systematically replace moving mechanical parts with moving photons. We're literally talking about shifting from the friction of the physical world to the absolute speed of light.
Okay, let's dive right into this. Here's our roadmap for The Explainer. We'll be hitting the photonic paradigm shift, computing and data storage, transforming global healthcare, next-gen transport and defense, future manufacturing and materials, and finally, a multi-trillion-dollar future.
Section 1. The photonic paradigm shift. Moving photons, not parts.
This slide really sets the stage. We've got this overarching narrative of legacy limitation versus photonic liberation. Look, the old mechanical world is just exhausting. It's hot, it's clunky, and it relies on moving parts that are inherently prone to friction, wear, and eventual failure. Photonic liberation, on the other hand, is silent, cold, and instantaneous. By utilizing solid-state light, we achieve zero physical friction. And why does that matter so much? Because completely eliminating physical friction radically alters the durability of hardware, and that permanently shifts global cost structures for maintenance.
Moving on to Section 2, Computing and Data Storage, Solving the Data Center Bottleneck.
So we all know the exponential growth of AI and unstructured global data is hitting a hard wall, right? We're constrained by massive heat generation, insane energy consumption, and severe memory bandwidth limits in traditional data centers. Well, Imagenta's solution is interference-based optical compute. Instead of relying on electronic logic gates that just bake themselves with heat, data comes in as structured light beams. These beams then interact inside an integrated photonic circuit. Because it relies on nonlinear optics, parallel operations happen simultaneously via optical interference patterns. It's kind of like ripples in a pond intersecting to do complex math. The mathematical results simply emerge from the light propagating, which captures immense value in high-performance AI computing with virtually zero heat.
And this brilliantly illustrates the bridge to next-generation networking. These are silicon-on-sapphire quantum transducers. The sapphire substrate gives you massive heat dissipation all the way down at absolute zero, minus 273.15 degrees Celsius. This standardized microchip physically catches an incoming microwave photon, literally like catching a baseball, converts it into a mechanical vibration on a silicon beam, and then translates that exact quantum state into an outgoing optical photon. It totally avoids those bespoke, handcrafted manufacturing bottlenecks we see today, giving us a highly scalable backbone for the imminent quantum internet.
But how do we store all this data? Forget spinning magnetic platters. Check this out. Lanthanide-Doped 3D optical storage. A primary laser excites nanoparticles inside a solid block of transparent glass. Then a secondary donut-shaped depletion laser comes in and suppresses that glow everywhere except the absolute infinitesimal center. This uses stimulated emission depletion physics to completely bypass the traditional diffraction limit of light. The result? Petabyte-scale nanoscale data compression permanently encoded in suspended, glowing nanovoxels.
95%. That is the potential reduction in data center electricity here. Why? Because this glass medium requires near-zero energy to preserve the data, and it's totally immune to water damage and temperature fluctuations. It basically guarantees centuries-long lifespans. Talk about radically slashing a data center's physical footprint and those astronomical cooling costs.
All right, Section 3, Transforming Global Healthcare, from invasive to instantaneous.
Now, the concepts of nanophotonics don't just stop at data. They are about to completely reinvent how we interact with the human body and manage hospital logistics. I want you to think about this for a second. How do you perform deep tissue surgery without making a single incision? Sounds like total sci-fi, right? But Imagenta actually has a mind-bending solution to invasive, tissue-damaging procedures.
It's called multi-photon non-invasive surgery. In traditional surgery, you've got the operating room, physical tools, collateral tissue damage, and of course, those expensive overnight inpatient stays. Multi-photon absorption, however, deposits energy exclusively at a precise subcellular focal region deep within the tissue. It completely spares all the surrounding areas.
This is a real game changer because it allows hospitals to convert complex, expensive inpatient procedures into fast, highly cost-effective outpatient appointments. And to track moving tissue during these procedures, they use acousto-optic deflectors. High-frequency acoustic sound waves propagate through a solid-state crystal, creating a dynamic optical grating. What this means is the scanner can snap the laser's focal point to random regions in mere microseconds. It provides inertia-free volumetric scanning that instantly adjusts for a patient's breathing during robotic surgery, which is fundamentally faster than any motorized lens ever could be. Plus, you can package it as a retrofittable unit for existing microscopes, saving hospitals millions in system replacement costs.
Pivoting to Section 4, Next-Gen Transport and Defense, Solid-State Situational Awareness.
Now, what's really interesting about this slide is the sheer necessity for reliability. In autonomous systems and on modern digital battlefields, mechanical failure is simply not an option. Yet, legacy mechanical LiDAR is bulky, fragile, and incredibly susceptible to vibrations and thermal warping. Imagenta replaces this with KTN electro-optic scanners. These microscopic potassium tantalite niobate crystals use blue light photon excitation and applied voltages to instantly alter their refractive index, bending the infrared laser beam with absolutely zero moving parts. Eliminating mechanical wear like that drastically drops replacement costs and actually helps solve the global autonomous driver shortage.
Over in the defense sector, this translates to wearable 3D battlefield AR visors. By using holographic optical waveguides, light literally bounces internally within a ballistic-rated visor until it's extracted by microscopic gratings right in front of the eye. It securely projects 3D topographical maps with sub-millimeter spatial alignment, highlighting friendly forces in green and hostiles in red. This massively reduces cognitive load, significantly mitigates friendly fire risks, and saves defense ministries a fortune by replacing heavy vehicle-bound radar consoles.
Let's look at Section 5, Future Manufacturing and Materials, Volumetric Creation.
We are rapidly moving away from slowly carving or stacking materials layer by layer and heading toward instantly manifesting solid objects using light. This is triplet fusion upconversion 3D printing. Low-power infrared lasers intersect in a vat of liquid resin. Sensitizers absorb this light and transfer the energy to annihilator molecules protected inside silica capsules. When those molecules collide, boom, they emit high-energy UV photons that instantly cure the entire 3D object all at once. By completely bypassing layer-by-layer mechanical tracing, this achieves continuous printing rates of millions of voxels per second. And since it uses standard diode lasers instead of massively expensive ultra-fast lasers, hardware costs are slashed by up to 70%.
We're also evolving from static parts to active materials. Think about legacy's subtractive manufacturing. Carving away at a block of material creates massive raw material waste, but femtosecond laser programmable matter changes the whole paradigm. It uses two-photon absorption to safely confine nanometer-scale reactions deep inside a flawless crystalline or polymer block without damaging the exterior surface at all. You can literally write internal 3D structures into the material itself, creating self-healing, active components that drastically extend the life cycles of incredibly expensive aerospace parts and biomedical implants.
Section 6, A Multi-Trillion-Dollar Future, Institutional Grade Scale.
As we transition toward our conclusion, we have to acknowledge something important. All this peer-reviewed physics is incredibly fascinating, but it only really matters if it can capture realistic market share and solve definitive commercial bottlenecks. And the market modeling we're looking at here is highly defensible. They are purposely avoiding those hyperinflated monopoly projections. For foundational bottleneck-breaking hardware like solid-state LiDAR for autonomous vehicles and optical cloud storage, they model a very realistic 10 to 15% market capture. That really grounds this mind-bending science in highly practical financial reality.
So, the crucial point is this staggering figure right here, an estimated £1.76 trillion in annual revenue by 2035. Bridging the gap between deep tech physical potential and commercial reality yields an incredibly robust, institutional-grade recurring revenue model across multiple global sectors.
Which brings us to the end of our explainer today, and I want to leave you with a final thought to carry forward. As we replace the exhausting physical limitations of mechanical parts with the infinite silent speed of light, which industry will you reinvent first? The photonic paradigm shift is absolutely here. Keep learning, keep questioning, and we'll see you in the next explainer.